Hello, my name is Natalie Patton, and today I will be discussing my summer research on phase change thermal energy storage. First, I'm going to be defining our problem and the reason we are doing this research. In many systems we encounter daily, such as heating, cooling, and ventilation systems in houses, electronics, or even things we don't encounter very often, like aerospace systems, we experience problems with transient thermal loads. They can cause significant damage to delicate systems or create large amounts of energy waste due to the inability to efficiently deal with high energy peaks. Enter phase change material systems, or PCM for short. These systems have the ability to handle the previously problematic thermal energy peaks and can reduce the total complexity and mass of previously mentioned thermal systems. They also give us the ability to have strict volume and mass limits. In order to utilize these systems, they must be built with charging and recharging the system in mind. Many previous works have focused on heat fluxes, like shown in the image on the right, but we will be focusing on applying PCMs in a system with fluid-moving heat loads, like shown in the image on the left. We will be using the Thermal Energy Storage Module, or TES for short. It will be made of PCM composites, which are good for dealing with unexpected heat loads as mentioned previously. They are capable of absorbing excess unnecessary heat and releasing that heat when the system doesn't need the entirety of its cooling capacity. We are expanding on SITMAV's initial work on the storage unit and simulating optimal conditions in a much shorter time frame than physically building the module. We have much more room to change the variables often to optimize our results for a variety of different circumstances. It is important to mention that we are just working on the TES module of this whole system, which is shown in the red box. The image on the left is a real-life model of the image on the right. We will be showing that there are optimal designs for these modules at specific timescales and heat loads. By designing with optimization in mind, we can minimize wasted resources. It is also important to mention that the image on the top left is an example of the model we are planning on creating, including the metal fins in the fluid channel. These metal fins absorb heat particularly well as they are made of conductors. This helps move the heat into the system efficiently. An essential part of optimizing our system is understanding Ragone plots. Our system has more energy storage than it does energy being put into the system, so we must also understand and visualize the impact of power on our system. Ragone plots give us the ability to look at the relationship between energy and power easily. This is the list of our conditions for our initial system. We started out with hexadecane as our PCM and aluminum as our metal conductor. It also has a flow rate of 0.2 kilograms per second and a difference of 5 degrees Celsius between the melting point of hexadecane and the inlet temperature. We use a 1,000-second timescale and rectangular geometry, which is 20 centimeters long and 10 centimeters wide. We created a multitude of graphs that emphasize different design traits. Shown on the left is a mass-dependent Ragone plot of hexadecane and aluminum, color-coded by 0 to 50% metal. As you can see, there are these little colored groupings that are each a thickness group, and the yellow vertical line is the maximum energy possible. The plot on the right highlights the 4 mm thickness and gives us a clearer picture of each thickness by highlighting it individually. Moving forward, we'll be looking at a variety of systems so that we can determine optimal conditions. So far, we have only looked at one material system, but as in electrochemical research and other work, other materials are available for comparison. This figure of merit, shown on the bottom right, is highly related to conductivity and is proportional to the heat flux in the case of constant temperature. We will continue to look at hexadecane with aluminum at different temperatures, but we'll also look at it with copper and graphite. We have also looked at lithium nitrate trihydrate with aluminum, copper, and graphite at different temperatures along with gallium. There are 4 main comparisons we need to make to optimize our system. First, we will compare the temperature differences, then the different PCMs with mass dependency and volume dependency in mind, then the different conductors, and finally compare mass versus volume dependency. Most of our energy is latent heat with minimal sensible heat. This latent heat is entirely reliant on the mass of our PCM, so with constant PCM, our energy does not change much. This is not the same case for power. Power is highly determined on the temperature gradient. The lines drawn on the right side of the graph are the Pareto fronts for each temperature difference at 4 mm thicknesses. The Pareto front illustrates the optimal conditions for each parametric sweep. Here is a close-up of the Pareto fronts in one graph, so it is easier to visualize the differences to see which graph excels, which in this case is clearly the 10-degree temperature difference. Next up is the PCM mass-dependent comparison, all with aluminum and a 5-degree temperature difference. In the close-up here, we can see that lithium nitrate trihydrate excels. However, it is important to note that lithium nitrate trihydrate does not do well with phase segregation, corroding, or supercooling. This makes it not particularly ideal for our situation regardless of the numbers. Under the same circumstances as the last graph, but with the volume dependency being highlighted, we can see different results. I will talk more about these results shortly. However, in this close-up, we can see that it's a tight race between gallium and lithium nitrate trihydrate, which both are pretty dense, so those values make sense. Next up is the conductor comparison, all with hexadecane as the PCM and a 5-degree temperature difference. In this close-up, we can see that aluminum and graphite both look pretty good and should be compared further. In this close-up, we can see that aluminum and graphite both look pretty good and need some further comparisons. Finally, here's the comparison between mass and volume Ragone plots. Here we are looking at gallium and aluminum at 10-degree temperature differences. The energy and power in our mass Ragone of gallium do not do well, with them being so small that we can't even see the time termination that we see in all of the other graphs with the same termination point. However, with the volume, we can see the termination in relatively high energy and power densities. This is related to gallium's high density. The higher the density, the better the PCM will do volume-wise. This is something to keep in mind when deciding which system to use. If there is little space to keep the system in, then a lower density PCM should be chosen. But if space isn't the problem, but mass is, then gallium would be a good PCM to choose. There are many pros and cons to each system depending on the design parameters. I have made a couple tentative conclusions. Volume-wise, a system with gallium as the PCM and graphite as the conductor with a 10-degree temperature difference is ideal numerically. However, realistically, gallium is expensive. We need to do more research on graphite and what kind of configuration we want it to have, because that changes the thermal conductivity. And this system would not work well in a space-limited environment. Mass-wise, it is close between lithium nitrate trihydrate and aluminum, and lithium nitrate trihydrate and graphite, with a 10-degree temperature difference. There are pros and cons to each component in each system, and they need to be studied closely to determine which one is better than the other. There is still a lot of research that can be done and will be done in this topic. There are different model geometries, such as cylindrical and spherical models, that need to be researched. There also needs to be more research on what kind of graphite configuration is realistically ideal for this system, as mentioned previously. Thank you, Dr. Schamberger and Mason Schulmeyer, for everything you both taught me this summer and for pushing me out of my comfort zone. And a very special thank you to Texas A&M MSEN O-REU for this really great opportunity. Here are my references, and thank you for your time.